Multivariable calculus, picking back up in lesson 12.5, our first day. We're still on example 3. We're trying to show that these two lines in space are skew. We mentioned earlier in the previous video that their direction vectors are not scalar multiples of one another. That's the definition of being parallel. So we know that these two lines actually are not parallel, but it's also quite possible that these two lines still do not intersect. Tell you what we can do. To check that, let's set x's and y's equal. If I were to set the x's equal, I'd get 1 plus t would equal 2s. If I were to set the y's equal, I would get negative 2 plus 3t for my first line. Set that equal to 3 plus s. And we can go ahead and solve now and, see. We could either solve with RTI 89 with a wonderful, system solver tool. But look, it's very simple to solve just with substitution just as well. If we did that, it's only going to take a moment. Just have to be careful as you have an s here. You don't want that to be mistaken for a 5. As I go ahead and distribute this 3, we'd get 6s minus a 3 is equal to 3 plus s. This would be 6s minus 5. And this would be 3 plus s. If I were to subtract an s from both sides, simultaneously add a 5, we'd have 5s is equal to 8. Very quickly we would solve and get s is equal to 8/5. However, if we were to plug that back in for our t, we could see very quickly that t would be 2 times that 8/5 minus 1. And that's 16/5 minus a 1, which is 5/5. So we'd get 11/5. So at this point, you can think, well, why in the world did you do that? Well, we're saying, look, if x and y are equal, which is what would happen if we had an intersection, our parameters would be these values, that s would have to be 8/5 and t would equal 11/5. But now let's go ahead and check what's happening in line 1. In line 1, our z would be 4 minus t. And then for line 2, we can see right here, our z would be negative 3 plus 4s. But you see, now we know what our t and our s actually would equal. Our t is 11/5. And of course, 4, if we were to get a denominator of 5, would be 20 over 5. 20/5 minus 11/5 would be 9/5. Likewise over here, if s is 8/5, we'd have 32/5, and of course this is negative 15/5. And as we would add this together, I think the most immediate thing that you're going to notice is you don't get the answer that we just came up with. Instead, you'd get 17/5, wouldn't you? And these are not equal. What does that mean? To intersect, not only would your x and y's have to be the same, your z's would have to be the same. So therefore, there's no intersection of these lines in space. We already saw that they're not parallel. So therefore, these lines are skew. Okay, so real quickly, let's finish up this lesson. We're going to talk about planes. And in 3 dimensions, if you're given a point and a vector, there is a plane that is orthogonal to the vector that passes through that point. The word orthogonal, remember, means perpendicular. And we could call this vector the normal vector. We could call this vector n. And so here's a plane. Looks just almost like a little slice of paper, or a little piece of paper right there floating in space. And we have a vector n, the normal vector. It would be perpendicular to that plane. It would make a right angle with it. But there is a point where we would be given specific coordinates for x, y, and z that would be on this plane. Remember, we can slide the normal vector anywhere we'd like. We could put it so that it would be perpendicular to that point. And then here's an arbitrary point, one that's not specifically named. It's just variables, x, y, z. And you can see in green, we have a vector in the plane. So let's find that green vector. We're going to do end minus beginning. And that's going to be x minus x naught, y minus y naught, and z minus z naught. So this is a vector in the plane. Well, I guess what I'd really like for you to remember is earlier in this unit, we learned about the dot product. The dot product, A dot B, was actually the length of vector A times the length of vector B, the magnitudes of those, multiplied to the cosine of the angle between them. Now we know that the cosine of 90 is 0. So for orthogonal vectors, for perpendicular vectors, what we're going to know is that the dot product is 0. Because the cosine of 90 is 0. So what are we getting at? We can take this vector n and this vector here and do a dot product. And because we know that this normal vector is making a right angle with this vector and with the plane in general, we can set this equal to 0. So what do we get? We've got a times x minus x naught right here, plus b times y minus y naught, plus c times z minus z naught is equal to 0. And guys, this right here is the equation of a plane in space. So it works out rather nicely and quickly. Let's do our last problem right here. We've got a point, x naught, y naught, z naught. And we want to find the equation of a plane. We're given this normal vector right here. So we'd like to write the equation of the plane and then find the intercepts and actually make a sketch of it. So what we're going to do is really say, hey, we can take vector n, that normal vector, and we'll have x minus -3 right here. We'll have y minus our y naught, which is 0. And we'll have z minus our z naught, which is just a 7. And we know that this dot product is 0. So we're going to have our 5, 2, and here's a -1. And this becomes x plus 3, y minus 0, or just a y, and z minus 7. And we'll set that equal to 0. And as we do our dot product, guys, we'll have 5 times x plus 3 plus 2 times y minus 0 plus -1 times z minus 7. Set that equal to 0. here is your equation of the plane. So that's wonderful. We're done with that aspect. But then we can wonder about finding intercepts. To find our x-intercepts, tell you what, let y equals 0 and z equals 0. So I have 5 times x plus 3. Here's a 2 times 0 minus 0. And then here's our negative 1 times 0 minus 7. And we'll solve this real quickly. This is 5x plus 15. This is gone. This is a negative 7 times a negative 1. That's going to be a plus 7. And it won't take us too long to solve here. 15 plus 7 is 22. I can subtract that. And guys, we've got an x-intercept right here. Let's find a y-intercept. To find a y-intercept, we're going to let x equals 0 and z equals 0. Well, what are we left with? This is 0 plus 3. This is, well, y minus 0 is just a y. And here we'll have negative 1 times, again, well, 0 minus 7 is negative 7. So this is 3 times 5, that's 15. Here's negative 1 times negative 7 is a plus 7. So 15 plus 7 is actually going to be 22. We can subtract that 22 and then solve. We'd get y equals negative 11. Finally, we can find our z-intercept. Our z-intercept is going to let x equals 0 and y equals 0. So we'd have 5 times 0 plus 3 plus a 2 times 0 minus 0. Then right here we'll have our negative 1 times z minus 7 is equal to 0. Well, this will be a 15. This is going to wipe out. Tell you what, we can even bring this over to the right side if you'd like to. That might be a nice way to do it. Just add a z minus 7 right here. Then add a 7 and you'd get z equals 22. So how do we graph a plane using these intercepts? Well, let's see if we could get some help here. Here's an x, y, z. And we don't have to graph this with super great accuracy. Negative 22 over 5. Well, it's going to be somewhere around over here, about negative 4 point something. It's, looking like that. Y going down to negative 11, well, that's going to be way down here. Oh, pardon me. I did the z-axis. Here, let's say y equals negative 11. That's going to be right over here. Then z equaling 22 would be way up here. So you could draw yourself a little bit of a triangle here. Make this dotted. And that would be like a little snapshot of what your plane could look like.